Welcome to Calculus 1, Lesson 1B.2, Limits Analytically. So in the last lesson, we talked about ways to either look at the graph or play around with numbers in order to get a sense of where a limit wants to go when an x value can't exactly touch where you're trying to get it to. Now, our gold standard for evaluating limits is going to be that direct substitution. When you can actually take that c, if you're taking limit as x goes to c, if you can take that c and just plug it right into the function and get an answer, evaluate at that c, then we know it works and we know we can get it. That's what we want to be doing, but we can't always get there. It turns out that direct substitution will work when the function is continuous at that c. So let's talk about what that means. The actual math definition of the word continuous is pretty involved, but visually, you can say a continuous function is one that you can draw all with one big stroke of your pen. If you can draw the whole entire function with one stroke of your pen, then you can say that it's continuous everywhere. It's continuous across all real numbers. Some functions are continuous only some places or only in most places. So we can also talk about what's it mean for a function to be continuous in a certain spot. So a function is going to be continuous at a certain point if it can be drawn with a single stroke of the pen just near that point, but it could still be broken somewhere else. So it's kind of like if you zoom in your window or narrow your focus or look at it with a magnifying glass. If there's some limited view of the function that can make it one stroke of the pen, then it's continuous in that little area, even if it might be discontinuous elsewhere. Let me show you what that looks like. Here's some examples of some continuous functions and also some ways for functions to be discontinuous. It doesn't matter if the function is pointy, jagged, or smooth. All of these I could draw with just one stroke of the pen. I can draw it without lifting my pen off of the paper. Okay? All linear functions are continuous everywhere. All quadratic functions are continuous everywhere. This squiggly function could be some kind of polynomial, right? This looks like a sine wave, or maybe a cosine. That's continuous everywhere. That looks like some kind of crooked absolute value. That's continuous everywhere, even though it's got that pointy spot right there. That's not a discontinuity. I can still get through that without lifting my pen, right? Not continuous would be like when you have that removable discontinuity. When you've got that little spot that divides by 0 until you try to factor and cancel. It's discontinuous here, but maybe if I wanted to talk about over here, in this little area, it's continuous, right? So I could direct substitute with my limits over here, even though I couldn't at this point. So it is not continuous at this point, but it is continuous everywhere else, everywhere but that point. You could also have, this is called a jump. So, you're going along and then you jump up to this other value. This is not continuous. I have to come here and then lift up my pencil and then go over here in order to keep going. Okay, it would be continuous here and here, just not at that one particular spot. Same idea with a gap, right? I'm picturing these 2 points here have the same y value, and these 2 points have a different y value. Doesn't matter, it's still discontinuous there. This one is still continuous for all of that and all of that, just not at these 2 points or anything in between. We're also discontinuous at asymptotes if we have an asymptote. So anywhere that is not that asymptote, so right here, arbitrarily close to the asymptote, you're continuous, no matter which side or which type you have. Just not at the particular x value where that asymptote lives. Now, to put that in more formal math terms and definitions, that's more involved and more complicated, and something that you would study if you took a class called real analysis, which is where you prove and develop and expand on calculus. It's pretty fun. It was one of my favorites. So overall, what's going to be our game plan for solving limits analytically? First thing you always want to do is try to direct substitute and just see what happens. What goes wrong, if anything goes wrong, because sometimes it won't. Check if any funny business happens, and I'll quantify this term funny business in a little bit. If not, your direct substitution is fine, right? If plugging in your C into that function doesn't result in anything horrible, then direct substitute and be along with your day. You're done. If something goes wrong, such as dividing by 0, then we want to try to use algebra to manipulate the function into something that can use direct substitution. And sometimes there might be other methods as well. Here's an example. Find the limit as x goes to 3 of 1 over x plus 3. Remember, your first line of defense is going to be the direct substitute. If I try to direct substitute 3 into this function, what do I get? I get 1 over 3 plus 3, which is equal to 1 over 6, and there's nothing wrong with that. So I'm done. Cool? If I look at the graph of this function, what's happening near 3 is it's going to have a vertical asymptote at -3, but I don't care about that because I'm going to +3. It looks like this. If this is +3, here's the y value of 1/6. This limit as x is going to 3 is making you want to slide along this curve until you land at that point. And there's nothing wrong with getting to that point and sitting on it. There's no hole to fall through, or there's no jump that you have to do at that point. All right. All right, so let's blow this up a little bit. Let's find the limit as x goes to 3 of x minus 3 over x squared minus 9. Now I'm going to rewrite this function by factoring the bottom. And by the way, when you're doing limit techniques to rewrite the function in a new way, you want to carry that limit operator along. This has to stay with you until you go ahead and take that limit, okay? So until you can get to a point that you actually can direct substitute, the limit operator has to stay, okay? It gets used up when we finally get it to where we need it to go. So here's the bottom factored. And then we get this nice cancel, and we find a new function that is equal to the original almost everywhere. Oh, by the way, what went wrong if I tried to direct substitute in the bottom? Should have showed that first. Direct substitute would be 3 minus 3 over 9 minus 9, which is 0 over 0. And that's funny business. Right, okay, so direct substituting wouldn't have worked for this one. However, when I factor and cancel, I get it into a form that can. Okay, so this function, 1 over x plus 3, isn't literally the same function as this one. It's equal to it everywhere except for +3. Okay, well, here I can direct substitute. Okay, at every step when you're doing a limit, check check and recheck. Can I direct substitute yet? It's like you're a little kid in the back seat of a car. Are we there yet? Are we there yet? Are we there yet? Every time you do a step, ask yourself, are we there yet? Can I direct substitute? Here the answer is yes. So when I go ahead and let x be 3, that is the moment that the limit operator can go away. So the answer to this limit is also 1/6. Cool. So here's some basic things we're going to want to know about our limits. Slide that over so you can still see. There we go. Oh man, I've got a bit of wonky notation here. I talked about this element thing before. When I say let B and C be an element of, well, that's a funky looking R. This R, this is called blackboard bold. That means all real numbers. So what I'm trying to say here is let B and C be any numbers, any real numbers. Okay, maybe I'll add that here. Blackboard bold R equals real numbers. Then I have an N. Let N be an element of funky looking N. This is a blackboard bold letter N. This stands for the natural numbers. And the natural numbers are 1, 2, 3, 4, etc. And there's this whole big debate, argument, dispute. I mean, we grab our torches and pitchforks over it. Us mathematicians have disagreements over whether 0 should be considered a natural number or not. So obviously, I'm in the camp that it should not. Because we have another name for the set that does include 0. That's the whole numbers. At any rate, some mathematicians are cool and some of them are not, is the moral of that story. What I'm trying to say here is let n be a natural number. So n could be 1, 2, 3, 4, etc. What would be the limit as x goes to c of b? Well, b is a number. B's not a function. So no matter what x is doing, whether x is close to c or far away from c, b is equal to b and b is equal to b, no matter what x is doing. So this is just b, stays b. How about limit as x goes to c of just a plain old x? Well, can I direct substitute a c into the function y equals x? Sure I can. When x goes to c, the x just becomes c. So plainly, that would be c. And then the limit as x goes to c of x to the n, well, can I direct substitute here? Does any funny business happen if I let x to the n be evaluated at some number c? No. A polynomial has its domain over all real numbers. So x to the n can have anything plugged in that you want. So this limit says just evaluate x to the n at c. So there it all is in arbitrary numbers and symbols. If your head is spinning a little bit looking at all those letters, let's try it with some concrete examples. So 1, 2, and 3 corresponding to 1, 2, and 3 down here. Consider limit as x goes to 2 of 3. Okay, so this, whatever appears here, we're thinking of that as a function of x. Okay, this is the function y equals 3, which is a horizontal line. Okay, now when x approaches 2, 2 is right here. There's x equals 2. Well, the y value is still 3, right? As far as this function is concerned, no matter what x is doing, the y is always 3. It doesn't care. So this is just 3. How about limit as x goes to -1 of x, plain x? Well, this is talking about the function y equals x, which is just a line. Okay, as x is approaching -1, here's x equals -1 right there. What is the y value wanting to do? It's wanting to go to -1 as well. So I can take this -1 and direct substitute it in to the x. And so I'll get -1. How about limit as x approaches 2 of x to the 5th? And I didn't draw a graph of this one, but you can picture it's going to look like, that's shaped something like that. And it's very, very steep. It increases very, very fast. But x to the 5th can be evaluated at any number you want, any number that you can think of. It could be evaluated at pi plus e plus square root of 2, for all I care. We're not doing that today because that'd be ugly. We're going to evaluate it at 2. Right? Nothing wrong with me going ahead and direct substituting 2 in for x there, evaluating x to the 5th at 2. And 2 to the 5th is equal to 32. Wait, it is, right? 2 to the 5th is 32. Yeah. Okay, so I know the way I present it up here with all the letters might be a little bit hard to look at and scary, but if you ever find yourself feeling that way, just swap those letters in with some numbers that they could possibly be, and it'll become a little easier to see. As you get higher in math, you get used to looking at things like this in the mathematical language. So those are some basics. Now I'm going to give you a big long list of things that happen with limits, and I'm going to call this the things we expect theorem. Now this is an ME term. If you go over to some other math teacher and say, oh, I learned about the things we expect theorem today, they're not going to know what you're talking about. That's just what I'm calling it for this class. So things we expect of our limits. First of all, what are our assumptions? We're going to let B and C be any numbers. N is going to be some natural number. F and G are going to be functions. We're also going to assume that there's some number C for which we already know the limits of F and G. We're going to assume those are L and K. So we're going to look at ways we can combine and change F and G to get things that we know how to take the limit of. The first thing is scalar multiples can come out. What do I mean by come out? So there's kind of some like implicit invisible parentheses around this, or a bracket, if you like. The B and the F in this way are kind of on the inside of this limit operator. When I say scalars can come out, I mean that when this scalar, this number B, which is multiplying by the function F, as long as it's multiplying by the whole thing, the entire function, it can come on the outside of the limit operator. From there, I can replace this expression with what I know it's equal to. I know that limit as x goes to c of f of x is equal to L. So this is B times L. So scalar multiples can come out. Here's another one. The limit of the sums is equal to the sum of the limits. So there in blue, there's the limit of the sums. So the limit of a sum of two things, that's equal to a limit plus a limit. So the sum of the limits, this is the sum of the limits because it is two limits being added. Okay, so that ends up being L plus K. If I combine those two facts together, then I get something for subtraction as well, right? If I change that to a minus, what I'm really doing is I'm saying, okay, I have a scalar. How much space for that? I got enough space. Limit as x goes to c of f of x. And I'm going to write this as plus -1 times g of x. Okay, well, the limit of the sum is the sum of the limits. Okay, so here is one thing being added. Here's another thing being added. Okay, so here's the limit of the sums. Here is the sum of the limits. X goes to c of f of x. And then this one is -1 times, oops, I forgot my limit. The big old plus sign in between. Okay, this one, I know what this is. This is L. By fact number 1, that scalar of -1 can come out. Okay, and now I've actually got everything I need to figure out what this is equal to. This is -1 times the limit for g is k. -1 times k I can write as minus k. All right, so f goes to L, g goes to k. F minus g is going to go to L minus k. But wait, there's more. It works for products too. The limit of the product is the product of the limits. Okay, so limit of the product in blue, product of the limits in purple. So that one is L times K. It's going to work for quotients also. The limit of the quotient is the quotient of the limits. So here's the limit of the quotient, and here is the quotient of the limits. That's going to be L over K. And this works as long as there's no divide by zero issue. And then the last one is that limits are going to obey function composition. And this is a little tricky to look at, but once we get working with it, it'll start to make more sense. What this means is as long as your f and your g are continuous, a limit operator can swap inside of the function. Okay, so we know that when x goes to c, g of x is going to go to k. So then the limit of f of g will be f of k. We'll see an example where that happens later. And when we get there, it'll be like, oh yeah, of course. Here's a corollary. Let me back up. What is a corollary? It's my camera first. So a theorem is a proven and established result in math. It's a very rock solid fact that you can stand on and work with. A corollary is something that follows very easily from a theorem, but isn't really interesting or strong enough to become a theorem of its own, right? So a corollary is a fact that follows very obviously and very naturally from a theorem. So fact number 7 here is going to be that polynomials can always use direct substitution. Okay, we can already kind of get a sense of that by the fact that polynomials have their domain all real numbers. There's no funny business in a polynomial. But it follows from the things we expect theorem because a polynomial is just sums and powers and multiples of x. All right? And then if I take two polynomials and divide those, if I take two things that can use direct substitution and divide them, then I can use direct substitution on the quotient as well. So rational functions, which are quotients of polynomials, those can use direct substitution as well, as long as you have no divide by zero issues, because those are quotients of polynomials. Example time. Let's say f of x is equal to 493 x to the 27th plus 96 x to the 14th minus 2x to the 9th plus 8. Find limit as x goes to 0 of f of x. Well, there's nothing wrong with x being 0 in this function. I can direct substitute. Okay, notice I'm taking the 0 and letting x become that. And that's why my limit operator is going away. Now, what is f of 0? It's going to be 0 plus 0 minus 0 plus 8. All right, so pretty ugly looking big scary polynomial there, but its limit at 0 is very easy to find. Now, I've got a question for you, and I want you to pause the video and see if you can answer this question before I explain it. When we are direct substituting a value in order to find the limit, are we evaluating or are we solving? When we direct substitute in order to find the limit, are we evaluating or are we solving? We are evaluating. There's no equation that we're manipulating there. When I go from here to here to here, I'm doing things that carry through what it's equal to. I'm not starting with a statement that two things are equal and then manipulating that to isolate a variable. That's what solving would be. I'm evaluating because I'm taking the 0 and plugging it in to the f of x to get 8 as the output. Okay, so evaluating is when you're going to put something in and get a number out. So that was evaluating. All right, so let's apply the things we expect theorem in excruciating detail before I show you how it actually is done in practice. All right, so first of all, I have an outside function which is the square root. And I have an inside function, 26x plus 9. So this is a composition of two functions. It's the square root of x and the 26x plus 9 are being composed. Now, square root of x is a continuous function, and so that limit can go inside of a square root. So that is equal to the square root of the limit as x goes to 0 of 26x plus 9. Okay, and that is by fact number 6. All right, next, what can I do? Well, there's a sum in here, so I can break that limit up over those sums, and each get their own limit. So 26x plus limit as x goes to 0 of 9. Okay, that is by, papers are out of order, there we go. Fact number 2. All right. Well, here we have a scalar on the x. So that scalar can come out. That's fact number 1. Right? And then this has unraveled to something that we can actually use the basic limits on. Watch that for you here. There we go. There's the basic ones. So now we have square root of 26 times, okay, now I can let x go to 0, so that's a 0, plus limit as x goes to 0 of 9. 9 doesn't care what x is doing. 9 is just always 9. Okay, so this is by fact number 1. This is by, I call this basic limits. And now we can just use our PEMDAS and evaluate normally. This is 0 plus 9 square root of 9, and that's 3. All right, that was tedious. Let's never do that again. You can, it's not wrong, but you don't have to show all of those details and all of those steps. How do we do it normally? Well, we go, I see that I have a function composition. Okay, so I know that my limit's going to be able to jump inside there. And then once I get inside, oh, I also have that nice corollary. This is a polynomial right inside there, right? So I know I can direct substitute. How we do this normally is we just notice that, oh, there's nothing wrong with x being 0 here. There's no funny business. So I can just go ahead and let x be 0. That was much faster. How about limit as x goes to 0 of sine of 2x plus 1. All right, so here's another situation where we've got a composition of functions. There's a 2x plus 1 on the inside of the sine. Okay, so I could show this intermediate step here if I wanted to. I could show that because sine is continuous everywhere, I can let the limit go on the inside if I wanted to. I don't have to show that step though. It's enough to say sine is continuous everywhere, 2x plus 1 is continuous everywhere, and so I know that I'm allowed to go ahead and direct substitute. So go ahead and let x be 0. So that'll evaluate to sine of 1, and whatever that is, it's some irrational number. It also matters, is that 1 degree or 1 radian? What mode am I in? Let's go to radians. Sine of 1. I don't know, some irrational number. How about limit as x goes to 1 of e to the 3x plus 4? Because it's not always about letting x go to 0. X can go anywhere it wants. All right, well, exponentials are continuous everywhere. 3x plus 4 is continuous everywhere. There's no funny business if x becomes 1 here. So this is another one where I can go ahead and just direct substitute. So I get e to the 7, whatever that is, irrational number. Um, when you're in a math classes like exact answers. Maybe in a science class, you got to think about your sig figs and how much you want it rounded and all that. As far as I'm concerned, this answer and this answer, those are done. We don't need the decimal approximation. Those are exact, and that's where you can stop. Okay. Okay, so how did I know that I can do that? What kinds of functions are continuous so that I'll be allowed to do that? When we first talk about continuous everywhere functions, these are functions that are continuous across the entire real number line. So any real number ever that you could think of. Okay, these are functions that don't break or don't have any funny business, no matter where x will go. That's going to be your polynomials, any odd root function like a cube root or a fifth root. Sine and cosine are continuous everywhere. Exponentials, absolute values. Arctangent is actually continuous everywhere. Arctangent is actually one of my favorite functions. Not really sure why. Okay, those functions can take in any x you could possibly imagine. So those are continuous everywhere. These ones are going to be continuous on their domain. So this category of functions, I'm going to say there's some chunk of the real number line that they're not allowed to go to. So that would be your even roots. So like square root, you're not allowed to put negatives in there. Logarithmic, not allowed to put negatives in there either. Arcsine and arccosine are only defined on a specific interval, right? It's got a very specific restricted domain in order to make sine and cosine appear invertible, right? So those are only continuous in a certain place. And then I'm going to call these ones continuous except at selected points. So there's just some kind of like little nitty-gritty points that have to be removed in order to say that these functions are continuous. Your rational functions are going to be continuous everywhere except for where they have either an asymptote or a hole, removable discontinuity, same thing. Okay, and then your tangent, secant, and cosecant, those are continuous everywhere except for the spots where they have asymptotes. And then I forgot about poor little cotangent. I forgot to write that down, so I added that in. Okay, so those ones are continuous except where they have those little oddities. Okay, so these can direct substitute anywhere. These can direct substitute anywhere that they're defined. These can direct substitute everywhere except for their asymptotes or holes. Okay, so when can we not direct substitute? Let's think about that a little bit more. Okay, finally, let me put a definition to this word I've been using, funny business. What does funny business mean? This, by the way, if you can't tell, that is an Emmy term. If you go to another math teacher and say, "Oh yeah," and then we got to look at the funny business, they're gonna be like, "What the heck do you mean? Have you been taking Emmy's classes again?" Um, so at any rate, here's our types of funny business. Here's our types of things that make us sad because we're not allowed to direct substitute when these happen. So we're going to pretend we have some functions f and g, and we know that they evaluate to 0 at c. And then I'm going to use a number sign just to mean like some random number that is not 0. If a limit would make me try to divide f by g, that would be asking me to do 0 divided by 0. This is called indeterminate. And when this happens, the limit could be anything. Maybe I'm just dealing with one or the other in either the top or the bottom. If it's asking me to divide some number by g of c, that's saying I want some number divided by 0. This is called undefined. When that happens, your limit is actually going to be plus or minus infinity. And we're gonna work with infinity in a little bit. Everything in this lesson is gonna be just focusing on finite numbers. In a future lesson, we are gonna work with infinity. Okay. What about if the 0 is on top? And we have 0 divided by some number. And actually, that's just fine. This is 0. This is just fine. 0 is allowed to be the answer to a question, right? We're allowed to get 0 as an answer, as an output. So this is not funny business. Cool. So now we know what funny business looks like. When it happens, what do we do? Our strategy is going to be to look for a way to manipulate your function into something that can use a direct substitution, right? Like direct substitution is what we want to be doing anytime that we possibly can. So here's one technique, and this is something that we've already touched on in a previous example. It's the factor and cancel technique. When you factor and cancel, the new function is equal almost everywhere and will have the same limit. Let's get a page. There we go. Okay, so since we've already been exposed to this strategy before, now is a good time to pause your video and see if you can figure out these two limits on your own. All right, so we've got these two different limits. Find the limit as x goes to 1 of f of x. Well, what happens if I direct substitute here? I will get 0 in the numerator, but that's not an issue. 0 in the numerator is not funny business. That's fine. The denominator is going to be, it's 2 times 1. Oh, there's actually nothing wrong with that. So direct substitution will actually work here. Plus 1, 1, minus 2. So this is 0, and then this is 2 times negative 1. So in disguise, that one wasn't even a calculus question. What if we try to go to 2? Well, then we've got some funny business, because when x tries to be 2, we're trying to divide by 0. 2 minus 2 gives us that 0 there. Well, that has the factor and cancel ability. So the function f of x is not equal to x minus 1 over x plus 1, right? This is not equal to this, but this limit is equal to this limit. Okay? And now this is something that we can direct substitute into without any funny business. So now that I'm going to go ahead and let x be 2, now I can finally get rid of the limit operator. okay? The limit operator is going to stay with you until you go ahead and let x go where it's trying to go. So we have 2 minus 1 is 1 over 2 plus 1 is 3. Okay, so factor and cancel. It's a pretty classic strategy for finding limits. Next one is rationalizing. Whenever you have a radical in your function, trying to either rationalize the numerator or rationalize the denominator can often get rid of your funny business. So let's try that. If I want to rationalize the numerator, I need to multiply by the rational conjugate of what's going on, okay? So the rational conjugate is going to just take one of the signs and flip it. So keep the sign of the first, change the sign of the second. And why can I do this? Because I am, in a smart and special way, multiplying by 1. I'm doing option number 2 here. Okay, when I multiply by 1, I haven't changed the value. So this limit is going to be equal to whatever it would be after being multiplied by 1, obviously. All right, now careful here because we're going to need to FOIL that numerator. So hold on to your butts. We're in for a little bit of a ride. As I FOIL the numerator, I have not let x go ahead and be 0, so the limit operator is going to tag along with us. Foiling is going to give me square root of x plus 1 times x plus 1 times square root of x plus 1. So that radical will come off. Then I'm going to have a minus square root and a plus square root. So those are going to kill each other off. They're going to cancel. And then minus 1 times plus 1 is minus 1. On the bottom, we need invisible parentheses around there. This is going to need to be distributed, but I'll do that on a separate line. All right. To help keep your notes and to help keep your work organized and to help me follow your work and give you the most partial credit possible, it's a good idea to just do one step per line. So I multiplied by 1 up here, and then the only thing I did to get from here to here is I FOILed. I left everything else alone. I rewrote it. I carried it with me. Okay. Next, I want to distribute here in the bottom. X is not allowed to be 0 yet, so the limit operator will tag along. So we'll have x times, you know what, actually, I'm just kidding. I don't want to distribute the bottom. What I want to do is I want to cancel the 1's on the top here. This is x plus 1 minus 1, so it's just x. All right, so now this looks like a factor and cancel type situation, right? This x is being multiplied by everything else in the denominator, and so that is allowed to be canceled with the 1 in the numerator. And when I do that, x has not been allowed to go to 0 yet, so the limit operator will still tag along. Now remember, as you're doing a limit, you're constantly asking yourself, are we there yet? Are we there yet? Are we there yet? Are we there yet? Okay, here, are we there yet? No, because there's a 0 here. This would be 0 times stuff, still dividing by 0. Here, before we canceled, it's 0 times stuff, so still dividing by 0. Now here, what happens if x is 0? My denominator is not 0 anymore. So now I'm going to go ahead and let x go to 0. It's like maybe x is like a dog. I love dogs. I train dogs. I'm training up a therapy dog right now. So anytime I can make an analogy about a dog, I will. X is a dog, and it really, really, really wants to get to that squirrel. Okay, 0. 0 is the squirrel. Right, maybe I'll draw a little picture. There's a stick figure dog. Okay, and he really, really wants to get to Mr. Stick Figure Squirrel. And you're holding him back on the leash. You're saying, no, no, Rover, you can't go to 0 yet until we get the right factor and cancel. At that moment, you let go of the leash and you let the dog go to the squirrel. When you let the dog go to the squirrel, that's when you get to finally stop writing your limit operator. So when x finally becomes 0 is when I stop carrying that operator along. Okay, so basically when you're working with only x's, when you don't have any other lettered constants in your question, the limit operator comes off when you're working with a bunch of numbers, right? There's a bunch of numbers. When you still got an x, the limit operator still needs to be there. So that's 1 over square root of 1 plus 1, which is equal to 1/2. Limit questions, when there's a bunch of complicated factoring and cancel, they can get long and ugly. Imagine if your function looked like square root plus square root over square root plus square root, and you were going for a limit where it would make that denominator 0. You would then want to rationalize either the top or the bottom, and you got to figure out which of those two things is the right one, right? And then you're going to have a lot of foiling and a lot of radicals to deal with. A question like this with a limit would be kind of long and ugly. So if you encounter that in your practice, good luck. Here's another technique we can use for finding limits. It's called the squeeze theorem. And squeeze theorem, believe it or not, this is not an ME term. This is an actual math word. If you go to another math teacher and start talking about the squeeze theorem, they'll know what you're talking about. The setup for this is, suppose that you're in a situation where you know that h is less than f and that's less than g. Okay, so you've got three functions that are greater than each other in that way. Okay, and then suppose also that you know that h and g are both going to go to some limit L. It ends up being, it must be the case that f of x is going to go to L as well. All right, to see this, let me draw you a picture. I need it where, first, let me consider this for just h and g. So I need to draw some function h of x less than or equal to g of x, where they both go to L. Okay, so that means they're meeting up at some point, even though g is usually bigger than h. So this point right here, this is going to be our, the x value is going to be c, and the y value is L. Let's draw g of x. G of x is the biggest one. G of x is going to be the purple. And then h of x is a smaller function. It's going to live below g of x, and it's going to meet up right here. Okay, now this other function f of x, we're assuming our setup says that it lives between h and g always. So f of x could be really, really crazy inside there. But if we know it's always the case that f has to live in between h and g, then f necessarily has to get squeezed onto L as well. That limit really can't go anywhere else when it's being squeezed together by H and G above it. Okay? So how do we use this in practice? Here's a couple of examples. Let's talk about limit as x goes to 0 of sine of x. Now, if I try to direct substitute there, I'm dividing by 0, and that's bad news bears. I don't see a way to rationalize. I don't see a way to factor and cancel. So as far as the tools that I've given you so far, those two techniques won't work. Can we try to use squeeze theorem though? Okay, notice that sine of x, no matter what x is, the sine of something always lives between positive 1, between negative 1 and positive 1. Okay, so sine of x over x is always between negative 1 over x and positive 1 over x. Okay. So when x is near 0, oops, it actually turns out I didn't leave enough room on the page to do this whole question. Okay, so our strategy here, it's gonna get really clever. We are going to make a triangle. The angle here, I'm gonna call this x. And I'm gonna say this angle x, it's gonna live in the unit circle. Okay, so if this is the unit circle, this here is the point 1, 0. Now let's extend this. So this whole distance here is going to be more than 1. I'm going to call this point A, and this point here is going to be B. All right, now you can show, if you get a little bit clever with your trig, you can show that this length here, the y value of the point B, is actually tangent of x. Okay, so we have a point 0, 0 right there. The coordinates of A are, well, this is a point on the unit circle where the angle is x. So this is cosine of x, sine of x. Okay, and then B, because this on the unit circle down here, the x coordinate is 1, and the y coordinate is tangent of x. Now, I'm going to consider 3 different areas. The first one is the smallest, the little triangle. What is the area of the little triangle? Well, the area of the triangle is 1/2 base times height. So 1/2, what is this length here? It's the x value of A, which is cosine of x, times the height, which is sine of x. Okay, next I want to consider the area of the pie slice, the sector. Now the area of a sector is 1/2 r squared theta. That's the area of a sector. Okay, so 1/2, the radius is 1, so r squared is 1, times the angle we said was x. So that area equals 1/2 x. Then the third area is going to be the bigger triangle. Doing 1/2 base times height. Got 1/2. The base is this length here. That is 1 because that point sits on the unit circle. And the height is tangent. And we can see from the way that we drew this picture that this is the smallest, this is in the middle, and this is the biggest. Okay, so comparing those areas, we know that 1/2 cosine of x sine of x is less than or equal to 1/2 x, which is less than or equal to tangent of x over 2. Now that 2, it's appearing in all three of those expressions there. Let's multiply everything by 2 and clear that out. And while I'm at it, I'm going to rewrite tangent as sine over cosine. For my next trick, I'm going to divide everything by sine. So I'm going to take all three of these expressions and I'm going to divide sine from them. So this one will be cosine, and then I'll have an x over sine, and then this one is just 1 over cosine. Now this is almost what we want to take the limit of, but I want to flip it. If you take the reciprocal, that will reverse the direction of your inequality. So the reciprocal of cosine is secant. Inequality is going to go other direction. And then reciprocal of 1 over cosine is cosine. Okay, so now we have a statement that is true for all x. Secant is greater than or equal to sine of x over x, which is greater than or equal to cosine. Actually, from the way that we constructed this picture, I'm 100% sure that this is true for all x, where the angle x would be in the first quadrant. I'd have to play with it to see if it's true elsewhere. But for x approaching 0, it will work. So now let's take a limit of everything. So limit as x goes to 0 of secant is greater than or equal to limit as x goes to 0 of sine of x over x, which is greater than or equal to limit as x goes to 0 of cosine. Okay, well, guess what? Cosine's allowed to take in 0. What is cosine of 0? It's the x value on the unit circle where the angle is 0. Cosine of 0 is 1. Secant of 0 is also 1. And so we have squeezed the limit that we want in between 1 and 1. Therefore, it must be 1. Cool, huh? For this one, it was also kind of borderline whether I was going to have enough space on the page to do this one. So of all things, I'm going to multiply by the conjugate of that numerator there. Why? Because sometimes when you're doing math, you just got to try random stuff. So I don't expect you to come up with a clever trick like that, but it does end up working for this question. So we're going to have a FOIL up there in the numerator. That'll look like this. Okay, after you FOIL the numerator, you're going to get 1 minus cosine squared. Now from there, remember your Pythagorean identity. 1 minus cosine squared is equal to sine squared. So I'll rewrite like that. Now I'm going to do something really clever. Again, I already know that the limit as x goes to 0 of sine of x over x is going to go to 1. Notice that there's a sign there and an x there. So I'm going to break up this fraction here, knowing the way that multiplication works. Okay, before I show what that looks like, think about this. If I had AB over CD, I could write that as A over C times B over D, right? Okay, applying the same logic here where A and B are both sine, and then C and D are x and 1 plus cosine, I can split that up this way. Okay, so one of these signs goes here, one goes there, and then we have the x and the 1 plus cosine. Cool? Well, the limit of the product is the product of the limits. I already know what this is. I can use the result that I got in the previous question. But look at this one. Can I let x be 0 here? Are we there yet? Are we there yet? Are we there yet? Well, sine of 0 is 0. Cosine of 0 is 1. So there's no divide by 0 issue here, is there? Let's say limit as x goes to 0 of sine of x over x. I'll give these each their own limits to contend with. Okay, so this one is 1 from our previous result. This one can be done by direct substitution. So sine of 0 is 0 over 1 plus 1. So this is 0. It all goes to 0. Cool. I had this third one here, but I've decided this video is already long enough. So I'm going to leave that third one as either a homework question or a challenge question. I haven't figured it out yet, but look for that if you think you can figure it out. So squeeze theorem can be pretty cool. Some of these problems do get pretty advanced. There's all kinds of hard stuff you could be asked with squeeze theorem that might be beyond the scope of what we really expect in a Calc 1. All I can say is I'd like to squeeze your mom's theorem, if you know what I mean. And there we have it. Now we know something about taking limits analytically. Keep practicing and have a wonderful day.